Beneath the western part of the Pacific Ocean lies an abyss whose scale defies human imagination. The Mariana Trench, with a depth of over 10 kilometers, opens like a dark rift in the Earth's crust, a place where the pressure is so brutal that a human body would be destroyed instantly, and where science long believed that life simply could not exist. For decades, what was known about this world buried beneath the water consisted only of fragments of data, cold numbers recorded in logs and echoes returned by instruments that never actually saw the bottom. Before discussing submersibles and high-pressure cameras, it is important to understand that initially, the trench was just an odd number in a column of measurements. To understand how we even began to suspect the existence of this abyss, we must return to a time when the deep ocean was practically a blank space. In the 1870s, the Royal Navy ship HMS Challenger set sail on a voyage that is now considered the first great global exploration of the oceans. This was not a heroic expedition in the romantic sense, but rather a methodical and repetitive business of measuring depths, sampling water and sediment, recording temperatures, and analyzing currents. Day after day, the scientists and sailors on board repeated the same procedure, turning the unknown sea into a series of data columns. Each depth measurement was a test of patience and physical strength. A lead block attached to an extremely long, graduated rope was lowered overboard and disappeared into the darkness. Then came the hardest part, hauling all that weight back up by hand, mark by mark, as the ship rocked under the tropical sun or through piercing winds in cold latitudes. It was a slow procedure prone to error, but it was the best technology of the time could offer. Every reading meant hours of effort and the constant risk of losing the rope, the weight, or even men overboard. Most of these readings told the same story: a wide and relatively uniform ocean floor covered in silt and sediment about 3 to 4 kilometers below the surface. The deep ocean began to take the shape of a vast, monotonous, and quiet plain, dotted here and there with volcanic rises and mid-ocean ridges, but generally more dull than legends suggested. However, in a remote region of the Western Pacific, thousands of kilometers from Japan and far from any coast, a routine measurement stopped being routine. The rope went down for a kilometer, then 2, then 3. It kept descending 4, 5, 6 kilometers, and the weight continued to sink without touching bottom. On deck, the sailors continued to let out the rope while the hull creaked quietly over a void of which no one had a clear idea, only a premonition of something immense and unknown beneath their feet. There were no detailed maps, no modern sonar yet, just a ship of wood and metal hovering over a blackness from which only the whisper of the wind on the surface could be heard. In those days, sailing into distant waters was already fraught with significant risks: storms capable of destroying a ship, invisible reefs, irreparable damage far from any port. To this was added the fear of the invisible. Tales of sea monsters with giant tentacles and impossible creatures were not just naive superstitions. They were a way of giving shape to ignorance, filling the void of information with images. The depths were imagined as a hostile space inhabited by deformed creatures and incomprehensible forces. In this context, Dropping a rope into an abyss that seemed to have no end must have been as unsettling as it was fascinating. Every subsequent swing of the rope was a reminder of how little was known about the world hidden beneath the keel. After a long wait, the lead weight finally reached the bottom. When they calculated the depth based on the length of the rope, they got an extraordinary value: 4,475 fathoms, just over 8 kilometers below the surface. Never before had such a reading been recorded in the oceans. This point was marked on maps with a name that would become legendary: the Challenger Deep, in honor of the ship that discovered the most fascinating chasm on the planet. Suddenly, the seafloor stopped being just a uniform plain. It had a point that seemed almost bottomless compared to the rest. At that moment, no one knew that this measurement did not even reach the true center of the abyss. The method based on ropes and weights was inaccurate and vulnerable to currents that could tilt the rope and change the calculation. For decades, this figure remained a record, but also a source of suspicion. Was this truly the limit, or did the ocean hide something even deeper? Many decades later, when technology allowed the use of sonar and other remote sensing instruments, scientists returned to the region. This time, they relied not on hand strength or the patience of sailors, but on sound pulses sent to the seafloor that returned with information about the underwater relief. The new data showed that the original Challenger measurements had only scratched the surface of an even deeper depression. The true lowest point of the Mariana Trench lies nearly 11 kilometers below sea level. To put this in perspective, a simple comparison is often used. If Mount Everest, at a height of approximately 8.8 kilometers, were placed at the bottom of the trench, its peak would still be submerged under nearly 2 kilometers of water. Down there, the pressure is over 1,000 times the atmospheric pressure at sea level. Every square centimeter of any surface is subjected to a weight equivalent to tons. The trench is not an isolated pit, but an elongated, curved structure running along the western edge of the Pacific Ocean, something like a scar marking the contact between two great fragments of the Earth's crust. At its widest points, it reaches nearly 70 kilometers across. One side drops off like an almost vertical wall. The other has a gentler slope, transitioning into abyssal plains. The Challenger Deep, despite being only a small section in this giant gorge, could hold dozens of skyscrapers stacked on top of each other without ever reaching the ocean's surface. From space, Earth looks like a relatively uniform water planet, a smooth blue sphere. But beneath this surface lies a topography as extreme as any continental mountain range. Underwater mountains, canyons, plains, and in the case of the Marianas, a chasm that pierces almost the entire oceanic crust. The origin of this crack is not an accidental fracture, but rather the slow and constant movement of the Earth's crust. The outer part of the planet is not a solid, continuous layer, but a mosaic of massive tectonic plates that move a few centimeters per year over the hotter, more plastic mantle of the interior. Where plates separate, magma rises, cools, and forms new ocean floor. This is where the seafloor is created. Conversely, where plates meet and collide, the crust cannot continue to accumulate indefinitely, and one piece must give way, sinking beneath the other. It is this process, the slow and silent subduction of one oceanic plate under another over millions of years, that carved the deepest abyss on the planet. On many oceanic boundaries, the older, colder plate sinks under the lighter one. This plate bends, cracks, and begins its slow descent into the depths of the Earth. This is the process of subduction responsible for the deepest ocean trenches on the planet. Every time one plate bends and sinks under another, the surface leaves a distinct mark, a long, narrow depression marking the point where the crust begins its descent back into the mantle. In the case of the Mariana Trench, the main player is the Pacific Plate, one of the largest and densest on Earth. For tens of millions of years, it has moved westward, slowly pushing its own crust to the edge where it meets the smaller, lighter Philippine Plate. The volcanic arc of the Mariana Islands runs along this boundary. There, the Pacific Plate is unable to push the islands outward. Instead, it bends and slides under the neighboring plate. At this point of inflection, where solid rock bends on a planetary scale, the trench is born, a colossal fold carved into the foundation of the ocean. This subduction pattern is not unique to the Marianas. Other plate boundaries bordering the Pacific show the same dynamics, and together form a large ring of trenches, island arcs, and volcanic chains known as the Ring of Fire. Nearly 90% of the planet's earthquakes and about three-quarters of its active volcanoes are concentrated there. Within this ring, the Mariana Trench is one of the most extreme and vivid examples of the power with which tectonics can reshape the Earth's surface. Understanding how the Mariana Trench formed is only half the problem. The other half begins when one tries to physically reach its bottom. At a depth of nearly 11 kilometers, the real enemy is not darkness or distance, but an invisible force that permeates everything: pressure. Even in something as mundane as the bottom of a swimming pool, it is already palpable. Just a few meters from the surface, your ears pop, and you feel a slight extra weight in your chest. At a depth of 10 meters, the pressure has doubled compared to sea level. If this same logic is extended to the scales of the Challenger Deep, the numbers stop being intuitive and become extreme. At the deepest point of the trench, the water column above it creates a pressure more than 1,000 times greater than atmospheric pressure, on the order of tens of thousands of pounds per square inch. Under these conditions, any object not designed with an enormous safety margin risks sudden collapse. The smallest structural flaw, an imperfect weld, or a bolt that wasn't properly calculated can become a source of catastrophic failure. Even equipment specially designed for the deep ocean has proven vulnerable. In 2014, an unmanned research vehicle exploring the Chromatic Trench at a depth of nearly 9,900 meters suddenly lost contact. The signal cut out, no further data was received, and the only things found afterward were scattered fragments of the machine. The pressure easily found its weak point. A comparison with modern military submarines is telling. These vessels, built for operation in combat zones, typically operate safely at depths of only a few hundred meters. Even the deepest diving models have strict limits. Long before reaching a kilometer, the risk of structural failure grows exponentially. On the other hand, The Challenger Deep plunges nearly 11,000 meters below the surface, an environment absolutely unreachable for any existing military submarine. Reinforcing the hull is not enough. One must conceive of an entirely different type of vehicle, designed from the ground up to withstand the pressure that ruthlessly crushes everything unprepared. In this context, a solution emerged that was as simple in concept as it was extreme in execution: the bathyscaphe. In the late 1950s, Swiss engineer Auguste Piccard designed the Trieste, a vehicle that combined two key elements. At the bottom was a thick-walled steel sphere, barely large enough for two people to sit together, huddled against each other. This tiny bubble was the only habitable space pressurized to surface levels. Above was a massive float filled with gasoline. The choice was not accidental. Gasoline is less dense than water and very incompressible, providing buoyancy even under extreme pressure. A support structure was attached between the sphere and the float, to which iron hoppers were fixed as ballast. The principle of operation was simple. The bathyscaphe was loaded with ballast to sink, and once at the bottom, it released part of this weight to float back up. There was no complex propulsion system or special comforts. Essentially, it was a sturdy sphere suspended from a buoyant tank. The rest was patience, calculations, and a significant dose of confidence that the equations underlying the design were correct. In 1960, two men climbed into this sphere to undertake a dive that would mark a turning point in history. Don Walsh, a U.S. Navy lieutenant, and Jacques Piccard, a Swiss oceanographer and son of the ship's designer, began their descent to the deepest point on Earth. Once the hatch was hermetically sealed, the sphere was isolated from the world. There was no room to stand. They could only look through tiny glass windows whose integrity depended on even the smallest micro cracks not becoming a fatal problem. As the Trieste began to sink, the sea above disappeared into distant memory. The journey to the bottom was not fast. As they descended, the temperature dropped and the pressure increased in a continuous gradient. Inside the sphere, Walsh and Piccard watched the numbers change on the depth gauge: 1,000 meters, 5,000, 8,000. Each number represented the layer of water accumulating above the steel hull. There was no way to open the hatch, no immediate retreat, no way to abort the descent in the usual sense. The only option was to hope the structure would hold until it reached the bottom. At a depth of nearly 9 kilometers, a sudden explosion shook the submersible. A sharp and loud sound echoed in the cramped cabin like a gunshot. For a few minutes, any theoretical calculations must have been overshadowed by the primal sensation of being crushed. It was later discovered that an outer plexiglass panel, installed as extra protection, had cracked under the pressure. However, the main cabin remained intact. The descent continued. After nearly 5 hours of diving, the Trieste finally landed on the floor of the Challenger Deep. The impact kicked up a cloud of extremely fine sediment that clouded the water in front of the small windows. For several minutes, one could only see something like a milky fog, liquid dust suspended in the darkness. As this cloud began to dissipate, the picture that emerged was no longer that of an absolutely lifeless mineral desert. According to Piccard's account, A creature resembling a flatfish about 30 centimeters long moved across the seafloor. The observation, seen through glass only a few centimeters wide and under immense pressure, was limited but sufficient to reach a crucial conclusion. Even at the deepest known point, life existed. Walsh and Picard remained on the bottom for about 20 minutes. They could not travel great distances or perform complex maneuvers. The main task was not to map the trench, but to demonstrate that it could be reached alive and returned from. After this short interval at the outermost point of the ocean, they dropped the ballast and began the ascent. The return to the surface took another 3 hours, traversing in reverse the layers of water that separated them from air and light. When they finally emerged, they had not only set a historical record, they forced science to reconsider the idea that life could not withstand such high pressure. Paradoxically, the success of the Trieste was also a kind of endpoint. The dive proved the journey was possible, but also made it clear that the level of risk and technical difficulty was enormous. For over half a century, while humanity conquered the summit of Everest and reached the moon, the bottom of the Mariana Trench remained practically untouched. No human set foot in the Challenger Deep again for decades. It was only in 2012 that the second human dive to the absolute bottom of the ocean took place, more than half a century after the Trieste. The protagonist was no longer a military project or a purely technological experiment, but a film director obsessed with the depths, James Cameron. Aboard the modern submersible Deepsea Challenger, he made a solo descent to the Challenger Deep. His craft was radically different from the metal cylinder of the Trieste. It combined lightweight and resistant composite materials, advanced electronic systems, high-density batteries, high-definition cameras, and an arm capable of collecting samples from the seafloor. It was not just about getting there, but about observing, recording, and bringing something from that world back to the surface. Cameron became the third person to reach the deepest point of the Mariana Trench, but his journey had an intentionally scientific focus. During the hours spent on the bottom, he filmed with 2D and 3D cameras, recorded the physical characteristics of the terrain, looked for signs of life, and stored sediments and rocks in compartments designed for extreme pressure. Every design decision for the Deep-Sea Challenger was dictated by the constraints of the environment. An elongated, almost torpedo-like shape to reduce drag during descent and ascent. A tiny pressure sphere barely large enough for the pilot to minimize the volume subjected to pressure, and redundant ballast and buoyancy systems to ensure a safe return. The result was a dive that combined exploration, technology testing, and scientific data collection. This dive had another effect that cannot be measured in meters or bars of pressure. It revived public and academic interest in deep sea trenches. What had been an isolated record since 1960 began to be seen as the beginning of an era, not a one-time event. From then on, a new generation of submersibles and expeditions began to visit the abyss more frequently. By the early 2020s, over 20 people had descended to the Challenger Deep, easily exceeding the total accumulated over the previous 50 years. Among the participants in these expeditions were researchers like Victor Vescovo and Hamish Harding, who set records for the number of dives and duration of work on the bottom, performing series of dives that allowed for data comparison across different dates and sectors of the trench. These new expeditions used high-resolution bathymetric maps, chemical and biological sensors, and more precise navigation systems than those available during the Trieste expedition. Instead of a single isolated dive, entire campaigns began to be planned. Multiple descents, slightly different routes, systematic sample collection, and the deployment of autonomous instruments that remained on the bottom for hours or days. Despite this, each descent remains a complex, expensive, and vulnerable operation. No technology has been able to turn the Challenger Deep into a routine destination. In practice, each dive remains a massive undertaking. It requires years of design and construction of the submersible, exhaustive testing of every component in pressure chambers and test tanks, independent certifications, and failure simulations. On the surface, support vessels equipped with cranes capable of carrying dozens of tons are needed, as well as laboratories for processing samples, redundant communication systems with the submersible, and specialized personnel in navigation, electronics, mechanics, logistics, and medicine. A valve failure, a tiny crack in the sealed hull, a short circuit in a critical system, or a ballast miscalculation could mean the loss of the craft, the data, and in the worst case, human lives. Although submersibles capable of repeatedly visiting the abyss already exist, the total number of hours humanity has actually spent on the floor of the trench is meager compared to the vastness of the place. Every descent offers only a narrow view, like a flashlight beam in a completely dark cathedral. Meanwhile, at first glance, none of these complexities are visible. Above the Mariana Trench, the Pacific Ocean looks like an endless surface of water, with no coastline or landmarks. It is all a uniform horizon, repeating waves, sky, and sea blending in the distance. But as soon as you leave this surface, the ocean stops being a uniform volume and reveals itself as a stratified space divided into distinct layers, each with its own light, temperature, pressure, and life forms. What from above appears as a single body of water is actually a superposition of different worlds. The first of these layers is the epipelagic zone, the luminous shell of the ocean. It extends from the surface to a depth of about 200 meters. This is a relatively thin strip compared to the thousands of meters below, but it plays the most vital role for life on the planet. This is the only layer of the ocean where sunlight is intense enough to support continuous photosynthesis. Here, solar radiation penetrates strongly, water is mixed by wind and waves, and the temperature undergoes daily and seasonal fluctuations that affect the entire marine system. In this epipelagic zone, billions of tiny organisms such as phytoplankton, cyanobacteria, and microscopic algae convert sunlight, dissolve carbon dioxide, and nutrients into organic matter and oxygen. They are the base of the marine food chain. Zooplankton, small fish, large predators, and ultimately many of the fisheries that humanity depends on all rely on them. On a planetary scale, their impact is even greater. Nearly half of the oxygen in Earth's atmosphere is generated in this layer, whose thickness rarely exceeds 200 meters. Every time a pulse of light reaches the surface above the Mariana Trench and passes through this upper layer of water, it activates, even if minimally, the same biological mechanism that supports the climate, regulates carbon, and allows the rest of the ocean, even its deepest parts, to be part of a living system. Phytoplankton becomes food for zooplankton, tiny creatures that drift with the currents, copepods, crustacean larvae, and tiny jellyfish. In turn, this zooplankton is eaten by small fish and larger jellyfish. These, in turn, feed larger predators such as pelagic fish, squid, and sharks. Thus, the marine food chain rises from its microscopic base just below the sunlight. Life in the deep sea depends largely on the productivity of this surface layer. Remains of organisms, excrement, tissue fragments, and aggregates of organic matter slowly settle like a dark rain, marine snow, which feeds the lower levels of the ocean. As you descend from the surface, colors begin to fade. First, reds disappear, then oranges and yellows, until only a deep blue filtered by the water remains. At approximately 200 meters, even this blue becomes dim. This is where the epipelagic zone ends and the mesopelagic zone begins, also called the Twilight zone. Life from above still exists, but it is so weak that it no longer allows photosynthesis to occur. The temperature drops rapidly, and pressure begins to increase more noticeably. In this constant semi-darkness, the first flashes of green and blue bioluminescence appear, emitted by the organisms themselves and piercing the darkness with short pulses of light. Despite the apparent darkness, the mesopelagic zone is extremely rich in life. Some estimates show that the biomass of fish inhabiting this zone exceeds the biomass of the rest of the ocean combined. Here you will find giant schools of lanternfish, animals that spend the day at depths of hundreds of meters and at night rise in massive vertical migrations to feed in the shallows. This daily migration of hundreds of meters up and down is one of the largest collective movements of animals on Earth, although it is almost never visible to the human eye. When you descend to about 1,000 meters, sunlight disappears completely. There is no difference between day and night. You enter the bathypelagic zone, also known as the midnight zone. The temperature stabilizes at a few degrees above freezing, while the pressure reaches values hundreds of times greater than at the surface. Ordinary submarines can no longer operate here. Their hulls are not designed for such pressure. And yet, this place is not a desolate void. In absolute darkness, flashes of bioluminescence multiply. Jellyfish, squid, fish, crustaceans, and worms turn the ocean into an inverted sky filled with moving points of light. This water zone, from 1,000 to 4,000 meters deep, forms the largest continuous habitat on the planet. Its inhabitants have shaped their bodies and behavior to survive in conditions that humans could not withstand. Their skeletons are light, sometimes reduced to minimal structures. Their tissues are flexible and adapted to pressure. Their metabolism has slowed down to conserve energy in an environment where food is scarce and arrives irregularly. Sensory organs have also been reimagined. Giant eyes optimized for capturing the slightest traces of light, pressure-sensitive organs, antennae, and tentacles that scan the water for chemical or mechanical signals. In this dark realm, light becomes an essential tool. Some fish have developed amazing eyes. For example, the barrel-eye fish has a transparent skull that functions like a dome through which its tubular eyes can rotate and look up in search of silhouettes against the faint glow falling from the upper layers. Other predators use light not only to see, but to attract. The deep-sea anglerfish carries a bioluminescent filament on its head, a tiny lantern that floats like a glowing worm. When prey approaches, attracted by this single point of light in total darkness, it suddenly finds itself in front of jaws full of long, sharp teeth. Meanwhile, the deep-sea dragonfish emits light along its body, creating a glowing silhouette that serves to disorient and lure prey before attacking. Even deeper, in still quieter parts of this zone, hangs the long-armed squid. Its central body is small, but its tentacles unfold like threads descending vertically for many meters into the darkness. It remains almost motionless, its arms extended like a net of sensors waiting for the slightest touch of prey. Occasionally, deep-sea cameras have managed to capture its ghostly silhouette, floating motionless in the water like an inverted kite tied to nothing. Even stranger is the siphonophore, one of the most mysterious creatures of the deep ocean. At first glance, it resembles an elongated jellyfish, with some species exceeding 40 meters in length, longer than a blue whale. But it is not a single organism, but a colony, a chain of genetically identical units, each specialized in a specific function such as movement, prey capture, or digestion. Together, they form a collective body that slowly drifts in the darkness, often emitting light along its entire structure. When a giant siphonophore coils in the depths, it paints undulating luminous patterns that seem alien to any terrestrial comparison. At a depth of about 6,000 meters, an almost invisible threshold is crossed. The bathypelagic zone ends and the Hadal zone begins, the exceptional territory of the great ocean trenches. Here, the water hovers just 1 degree above freezing, and the pressure approaches values 1,000 times higher than atmospheric pressure. Every square centimeter of any surface feels a force that, on a human scale, would be unthinkable. Despite this, the Hadal zone is not completely isolated. Along the bottom of the trench circulate currents of cold, very dense water that sank in the polar regions and slowly crossed half the planet before reaching this point. These deep water masses carry dissolved oxygen with them, maintaining a minimum level of habitability even in the most remote corners of the ocean. This slow and silent circulation is the thread that connects the abyss with the rest of the Earth system. In a place where light never reaches, life can no longer depend solely on food falling from the surface. Marine snow remains important, but it is not enough. At certain points on the ocean floor, fluids rich in chemical compounds such as hydrogen sulfide, methane, and other reduced elements leak from the oceanic crust. There, microbial communities use these compounds as an energy source, converting inorganic matter into biomass through chemosynthesis. This is a process analogous to photosynthesis, but fueled by chemical energy rather than sunlight. Much less efficient, yes, but sufficient to support small food chains in an environment where every resource counts. On this microscopic foundation, distinct communities are built, almost invisible on a human scale. Among the most characteristic inhabitants of the Mariana Trench's Hadal zone are snailfish, small animals with soft bodies, milky white color, and minimal bone structure. Their gelatinous tissues and sparse bones are an extraordinary adaptation to the crushing pressure. By reducing rigid parts, the risk of fractures and internal collapse is diminished. Snailfish have been recorded in the Mariana Trench at depths of about 8,000 meters. They moved in smooth motions along the bottom and between the walls of the underwater valley. However, below approximately 8,200 meters, no living bony fish has ever been observed. This depth, as far as is known, is the definitive biological limit for this group in the deep ocean. It is believed that beyond this limit, pressure alters proteins and cell membranes in vertebrates to the extent that their physiology stops functioning. What for humans is just a number, for marine life turns into an invisible wall, a depth range that some lineages managed to conquer and others did not. At the very bottom of the Challenger Deep, where the trench reaches its greatest depth, life seems to shed everything unnecessary. Large fish disappear, complex bodies become rare, and the ecosystem simplifies in appearance, almost reducing to microorganisms and a few specialized invertebrates. Among the latter, amphipods stand out, small crustaceans that appear fragile but are extremely resilient. Observation cameras baited with pieces of fish recorded swarms of these animals descending on the food in minutes, demonstrating that even in the most remote abyss, the opportunity to eat is never missed. However, the amphipods visible near the bait tell only part of the story. The most common method of observing life in trenches is to lower cameras to the bottom with bait, wait a few hours, and retrieve the equipment. This means most of the resulting images show a small circle of artificially lit terrain and a community filtered by the type of food offered. It is known that scavenging crustaceans flock quickly to this free resource, but that doesn't mean they are the only inhabitants. They are simply responding to an available stimulus during the brief interval when the light is on. More inconspicuous, clinging to the substrate itself, are perhaps the strangest organisms in the entire abyss, xenophyophores. At first glance, they look like shapeless blobs, jelly-like masses covered in mud and attached to rocks or sediment. But each of these structures corresponds to a single giant cell capable of reaching the size of a human fist. To build their delicate shells, these organisms agglomerate tiny particles of sediment, mineral fragments, and remains of other living things. Then they filter from the water the minute organic particles that make up their food. The interest generated by xenophyophores goes far beyond simple biological curiosity. Their ability to maintain functional, flexible, and renewable cell membranes under pressure that deforms most known structures offers important clues for materials science, biotechnology, and medicine. Understanding how they protect and repair their DNA in these conditions could inspire new strategies for dealing with surface cell damage, from tissue preservation methods to innovative approaches for treating diseases related to genetic stability. In a sense, Each giant cell at the bottom of the trench acts as a natural laboratory where life tests solutions not yet imagined on land. Despite the technological progress of recent decades, our knowledge of this world remains fragmentary. Most available data on the deepest trenches come from a very limited number of dives and automated cameras that capture only tiny areas for short periods. At the bottom of the Challenger Deep, it is believed that only microorganisms and invertebrates can withstand the extreme conditions. But even this claim is based on limited evidence. Humanity has almost never spent enough time there to state anything with absolute certainty. This lack of observation makes the trench a territory full of uncertainty. What other undescribed species inhabit its walls and recesses? What biochemical mechanisms allow a cell to continue functioning under pressure of up to 16,000 pounds per square inch, temperatures near zero, and total darkness? What ecosystems form around, yet undiscovered chemical leaks? Every new dive, every deployed camera, every collected sediment sample adds a piece to a puzzle that remains almost entirely empty. The question also remains open as to the extent to which human activity is beginning to alter this supposedly pristine environment. Recent studies have found microplastics and other pollutants in deep sea organisms, including amphipods caught in the trenches. While the reference article focuses on marine life and exploration, other research has shown that even in the most remote parts of the ocean, the products of modern industry and consumption are slowly seeping into the depths. Far from being a sanctuary untouched by our presence, the abyss is beginning to show traces of the surface. At the same time, the prospect of economic exploitation of the ocean floor raises questions about the impact of such activities on ecosystems that are still poorly understood. Any disturbance of sediment, any modification of deep sea currents, or the chemical sources that support chemosynthesis could cause unpredictable consequences for a very delicate ecological web. In an environment where processes are slow and regeneration can take centuries, damage would effectively be irreversible on a human scale.